Hi, welcome to another edition of Calculus 2. We are going to continue our conversation about Taylor polynomials and approximations and Maclaurin polynomials and approximations. So you remember last time we talked about the fact that in high school you go through algebra and you learn about the powers, and the polynomials are made out of these powers, and then you come across some other functions: rational, radical, exponential, trig, logarithmic, and so on, and you wonder if they can be written to look like a polynomial. So last time we answered this question. We said there is a simple recipe. We described the Maclaurin formula, how to derive it for any of these functions. So aside from that point of curiosity, what is the point of this activity? What do we gain out of it? Well, when we want to calculate a function, we have to reduce it to these basic terms: multiplication and subtraction, addition, and so on. So when we come across sine of x, exponential of x, and so on, how do we actually calculate it? How does a calculator calculate these quantities? So what we are after is actually very close to that question, and there are courses you might take later on, typically called numerical analysis, where you go into much more depth than what we are doing right now. But let's go ahead and do some simple examples so how we can put these polynomials to use for approximating these functions. So you remember last time we talked about sine of x and how to approximate it by a polynomial. So sine of x, let me take these pictures off now, these graphs. So sine of x, you're familiar from trigonometry, looks like this wave, and the question is, how do we approximate it by polynomial? Because that is the only way we can actually calculate these functions. So simplest approximation is to approximate it by this 45-degree line around the origin. Sine of x is pretty close to this y equal to x. In fact, in your physics classes and introductory calculus classes, you refer to this fact that sine of x is approximately x for small angles. So in the physics classes, they typically refer to this as small angle approximation. When you talk about pendulum and some other physical apparatuses, you actually make use of this approximation. Okay, so what does it mean to say we have an approximation? Well, of course, you see there is a gap between this blue line and the red curve. And the further out we go, the bigger the gap gets to be. So our approximation is only good for vicinity of origin when x is a small number. So if I am at a certain x value, what is the gap between the actual and the approximation? Well, simply calculate both of them and subtract it, and that's the amount of error you're going to make if you're using the polynomial for the actual curve. Well, what if we want a better approximation? So we have to spend some effort. So next one was to include a cubic term, and that's what brought us this green curve. This green curve stays closer to the red one for a longer time than the blue one did. Of course, it comes at a additional cost. We have to calculate x cubed over 3, subtract it to get this blue one, and so on. You said if you want to go up to degree 5, you get this purple one. It comes even closer than the green one, but at the cost of one more term here. You want something better, include power 7. Now we have this black one all the way up to pi almost. It does a pretty good job. So two issues comes up. One is, if we use these polynomials instead of the actual function, how much error are we making? Well, that's a simple question. Calculate both of them, subtract them from each other, and that's the amount of error you're going to make. So if you want to know how far off this black from the red one, say at x equal to 4, you put the 4 in sine of x. Of course, this is in radians. Remember that everything here is in radians. So you calculate sine of 4, and you put number 4 in whichever of these approximation you're using, let's say degree 7, you go through calculating this one, and that's what the degree 7 approximation is going to give you. If you subtract it, well, that's the amount of error you have. So that's a straightforward calculation. More difficult than this is in reverse. In a real life calculation is typically we want to have a function that's not so familiar to us. It's not as familiar as sine of x. We want to calculate it, and we want to know how far out should we go. Is this enough, or should I go to the next one? Should I go to the next one, and so on, for my error to be below a certain value? Well, can we do trial and error until we know? Well, that is assuming that you know what the function itself is, and in many cases the function itself is not accessible to us. It's only accessible through these approximations. So the second question turns out to be quite a bit more complicated than the first one. So let's go ahead and do an example of this thing. I'm going to look at a problem we did last in the previous lecture. So we talked about Maclaurin expansion for the logarithm of 1 plus x. Let's go ahead and practice a problem related to that. So to do this thing, we have a few theorems, one attributed to Maclaurin, another one to Taylor, and several other people have their names on it, so it's a joint project of half a dozen mathematicians in some sense. This theorem tells us about how much error is there in actually using a polynomial in terms of instead of a function. So suppose we have a function f, like that logarithm of 1 plus x, and suppose it has n plus 1 derivatives in an interval containing points of interest 0 and x. So if we take f of x and make a polynomial for it, Maclaurin polynomial, and we go as far as degree n, well, we are making an error. There is a remainder. We typically refer to it as Rn of x. So let me go to this picture and show you again. Let me remove the clutter and just have one of them. Okay, so this is the black one is degree 7 approximation for the sine. Well, there is a gap here. That gap is the difference between what the polynomial shows and what the function actually is. So that gap, we are referring to it as a remainder. So in this case, it's going to be remainder for polynomial that goes up to degree 7. We can call it R7, for example. If I had decided to stop at 5, then my gap would have been the gap between these two functions. I would have called it R5. At different x values, the gap is a different number, so that's R5 of x. That's what we are talking about here. Okay, so we have a polynomial, and whatever is left, or the error we are making, is called the remainder. The polynomial, we have the recipe for the polynomial. We take the function, evaluate all of its derivatives, evaluate that at the origin for Maclaurin. All of these things are evaluated at 0, and nth derivative is multiplied by x to the power of n divided by n factorial. That is the ingredients of the Maclaurin polynomial. Now what's new here now is a formula for the remainder, that gap. What is that remainder? The remainder looks very much like the next term of this polynomial, except for one major difference. So we see that we have x to the power of n over n factorial. So the next one would have been x to the power of n plus 1 over n plus 1 factorial. The thing that is different is that this next derivative, instead of being evaluated at 0, it's going to be evaluated as at some point between 0 and your quantity x. So what Maclaurin says is that that gap that you see, that the error that you see, is always equal to such a term. The only thing about it is that we don't know where this z is. If we knew, well, we will be almost done, but typically we don't know where that is, except that we know it's between the origin and the point at which you are evaluating the function. Okay, however you go ahead and evaluate this remainder is going to give you an estimate of the error. So many of these problems refer to an error, and that typically refers to how you evaluate this remainder term. Okay, we said two types of problems. One is simple one. We have a function given to us and we are told to calculate the Maclaurin polynomial up to a certain term, and then we want to know how accurate is that if you are using it for calculating the function at some specific number. Okay, so that was the issue of you calculate the polynomial, you calculate the function with your calculator or somehow, and you take the difference of the two, and then you're done. Much more complicated issue is the reverse. Suppose they tell us that we want to have the quantity calculated with an accuracy of a certain level. That is, our error wants to be less than a certain given number. So suppose I want to calculate logarithm of 1.2 by using a Maclaurin polynomial, but I want to make sure that my error is less than 10 to the power of minus 5. Question: how many terms do I need to use? What should be the exponent of the very last term we use here? So that's one level higher up than the first one. Okay, let's go. After this, we talked about Maclaurin series last time for logarithm of 1 plus x. We said it has a very simple format to it. X over 1 minus x squared over 2 plus x3 over 3 minus. So the sign is alternating. The denominators are just natural numbers. No factorials got cancelled out. We just have 1, 2, 3, 4, 5, and so on. So this thing is an approximation of logarithm of 1 plus x. Better approximation you want, you just include more terms in it. We said in this particular case, x has to be a small number for approximation to actually work. We cannot just use any number we want. Rather, we have to be careful about the quantity x itself. So right now, when I'm asking for logarithm of 1.2, it means my x is 0.2. Okay, the function is 1 plus x. If the input is 1.2, it means x is the number 0.2. So if I put 0.2 in this, I get an approximation for logarithm of 1.2. So let's go ahead. So first, we know that for logarithm of 1 plus x, we have the Maclaurin polynomial. It goes like x over 1 minus x2 over 2 plus x3 over 3, and so on we go. And then we want to stop at x to power of n over n. The question is it the plus or minus? Well, here is one way to resolve it. If n is even, we have to subtract. If n is odd, we have to add. And one way to handle that is to write this thing as, say, n minus 1. Use that always to check the first couple of entries to make sure that everything is working right. Okay, this is the Maclaurin polynomial. Okay, next question is, well, what is the remainder? That's what is going to determine what our error is going to be. But before we do that, let's go do the simple one. So suppose we are told just use 3 terms of last term is power 3, let's say like that. The power 3 is the last one to be used, and since we are looking at the logarithm of 1.2, when you put set 1.2 equal to 1 plus x, that tells you that x is 0.2. So if you want to calculate m3 at 0.2, you get 0.2 over 1 minus 0.2 squared over 2 plus 0.2 cubed over 3. So you can use your calculator, or you can use your here just as a reminder, you can also use this let me open another one. So you have 0.2, you can use this as a calculator. You see what you are entering. So so we get 0.18266 and so on. So let's go ahead and enter that. In our sheet we have 0.1826. So what we have here is 0.18266 and so on. So you can write it to say 4 decimal place or 5 decimal place according to how the problem wants it. And then so here's our approximation. Logarithm of 1.2 is approximately 0.18266. Well, how much is it exactly? Well, since we have access to logarithm, that is, you have a calculator that somehow magically actually gives you the logarithm, so we can go ahead and calculate this and see. So my calculator says 0.182321 and so on. And by the way, again, if you don't have your calculator available to you, you can always come and use this one. So ln of 1.2. So it gives me a couple of more digits than what my calculator does, actually 2 digits extra. So anyway, so we have these two, and if you want to call this thing quantity A and this one quantity B, excuse me. So A minus B, that is the error that we are making. You can write A minus B or B minus A. So 0.000345. So we have the quantity 0.18266. That is what our polynomial gives us. The question is, how much are we off? That's called the remainder, or Rn, to give us the actual value of the function, which was the logarithm of 1.2. So that is 0.18231. So my Rn is going to be 0.18231 minus 0.18266, and so the difference is going to be so this becomes 5, and I write it correctly. So this is sorry, is that what we had on that page? Let's see. Yes, I subtracted the other way. So if I write logarithm of 1.2b minus the polynomial, I get this quantity, which is indication of the remainder or the error we are making. Okay, so you see that we are okay to 3 decimal places, and after that things depart from each other. This one is 6 and this one is 3. And the question is, what if I want to have 2 more digits? What if I want the error to be less than 10 to the power of minus 5? And that's what we said is going to take a bit more work. So this is the what's the accuracy of M3? The accuracy or the error is about 0.0004. Now, next question. How far do I need to go? So here I stopped at 3 terms. Next question is how many terms should I add to this thing so that my error becomes less than a certain quantity. So this one we say by Maclaurin theorem, the remainder after n terms is used was x to power of n plus 1 over n plus 1 factorial times n plus first derivative. The only catch here is this derivative has to be calculated at some point z, and z is between 0 and x, and typically we don't access z directly. We don't know where it is, otherwise we wouldn't have the error. Now, well, what was the formula for this derivative? So in any given problem you have to go ahead and find out what the derivative is. So here we have written in the previous lecture, we have first a few cases of the derivative. So if I want to write derivative nth derivative, what is the formula for nth derivative? We come and detect a pattern here. We see that this exponent is same as that, and this is factorial of a number 1 less than that. So it becomes n minus 1 factorial times 1 plus x to power of minus n. And we said this minus or plus goes according to, if this is odd, this is positive, and if it is even, it's negative. So the way to do that is, for example, with the exponent n minus 1. To write this thing in a little bit more legible way, this is going to be minus 1 to power of n minus 1, n minus 1 factorial, and if you wish, you can put this thing in the denominator, 1 plus x to power of n. That's the formula for our nth derivative, and sometimes that becomes very hard to find. In this case, it was not all that bad. In the formula for the remainder, we need fn plus 1. So I'm going to enter fn plus 1 there. So fn plus 1 is going to be, so when we have n plus 1, this becomes n factorial, and denominator becomes n plus 1. So let's go ahead and write that here. So I have fn plus 1 evaluated at some unknown place z. That is going to be minus 1 to power of n factorial over 1 plus z to power of n plus 1. So, and this is particular to the problem that we are looking at. This is general. So I'm going to take this and plug it in that one, and now my Rn becomes x to power of n plus 1. Then I have minus 1 to power of n. Well, let me write it one at a time so that things do not get mixed up. The first piece is n plus 1 factorial here. So these two terms I just copied through. Now I take this one and copy it here. So I have minus 1 to power of n factorial over 1 plus z to power of n plus 1. So the calculation is a little bit involved, but I'm sure you can do it. So Rn, for the logarithm case, the simplification is that these two cancel each other, and I'll have minus 1 to power of n, x to power of n plus 1, and then denominator I have left with an n plus 1, and then I have 1 plus z to power of n plus 1. Okay, so for logarithm problem, that is what the remainder is going to look like. Now in our problem, we were going to look for logarithm of 1.2. So that means x is 0.2. And we know z is between 0 and x. So 0 and 0.2. So let's see how can we use this thing to whittle down Rn and make it clear for ourselves as to what it is. So the leftover remainder is minus 1 to power of n. Then x is 0.2 to power of n plus 1. And then denominator I have n plus 1. Denominator I have n plus 1. And well, z is between 0 and 0.2. If I come close to 0, this denominator becomes smallest possible, so Rn becomes as large as possible. If I go toward 0.2, I'm increasing the denominator, and as a result Rn is going to decline. I want my Rn to be less than 10 to the power of minus 5. So for that reason, to err on the conservative side, I say, okay, I'm going to use 1 here, and I'm going to hope that this whole thing, so I want Rn in absolute value to be less than 10 to the power of minus 5. That is how to assure ourselves that our accuracy is within the required range. So that means I want 0.2 to power of n plus 1 over, and now I have n plus 1 less than 10 to the power of minus 1. I want to find the first n where this happens. Okay, this is a kind of inequality we don't come across all that often in college algebra or pre-calculus. The way we solve this type of inequality is that by trial and error we can consider consecutive values of n until this fraction falls below that. It's kind of an inequality that is a bit hard to solve. Okay, since we have access to a nice calculator, let's see how can we use this to how can we use the calculator to handle this. Now on a calculator, on a graphing calculator that we are using, meaning Desmos, 10 to the power of minus 5 is going to be hard to see. You have to keep, this is a tiny number, and if you want to keep zooming to see it, it's not going to be all that comfortable. So let's do the following. Let's take a logarithm. This is just common logarithm, that's logarithm in base 10 of 0.2 to the power of n plus 1 over n plus 1, and we want this to be less than logarithm, again it's in base 10, not natural logarithm, use base 10 so that it's easy. So I want logarithm of 0.2 to power of n plus 1 over n plus 1 to be less than, now what's the logarithm 10 to the power of minus 1? Do you remember that? That's of course just minus 5. So we did all of this so that instead of dealing with a small number like this, I have a easy to see number like -5. So now I can go ahead and use decimals to solve this inequality. How do I do that? So let's go back here. Which one of them was this? Let's see. No. Okay. So the remainder, well, this is a logarithm of remainder, so let me call it something else, maybe t or something. So we took a logarithm of that. That's how it looks like. The logarithm of that expression in terms of n. This is a whole number n here. It can be 0, 1, 2, 3, 4, 5, but the calculator, it graphs it for all values of n. Okay, we want this to be less than -5. Less than -5 means below -5. So when you say y equal to -5, here you see this blue line, that's where -5 is. We want the red to be below -5. So the intersection as at this point is a smidgen past the point n equal to 5. Okay, so since we want to be less, we have to go to the next whole number. Okay, so here the intersection is as 5.036. To err on the conservative side, we come to this point that is n equal to 6. So if n is equal to 6, our Maclaurin series is going to be what I have typed here, and when you calculate this thing, you get 0.18232. If you actually calculate the logarithm of 1.2, you get this one. You notice that the first 5 decimal places are exactly the same. Now, what if I had calculated one less? That is, I had stopped here. Well, my accuracy, I will be losing the very 5th digit here. Instead of 3.2, I'll go to 3.3, and I'll be slightly off. So here is a practical way of solving these problems. You take the logarithm of this, common logarithm of that, take a logarithm of the accuracy that you want. So we wanted 10 to the power of -5. So we draw the line -5. We find the intersection. We go to the next whole number. So here's I'm at 5.036. n has to be a whole number, so we go n equal to 6, and that is the answer to the problem. So we find out that n has to be 6 for the condition to be satisfied. So when first we started with just 3, n equal to 3, and we said that the error that we have starts in the 4th decimal place. Now we wanted the error to be less than 10 to the power of -5, and the cost was that we had to go to 6th term. An alternative way of handling this type of problems is just to do trial and error. If that is more convenient for you, start with n equal to 1, then 2, then 3, and so on and so forth, until the fraction becomes less than the accuracy that is required. Then you are ready to declare the answer, in this case n equal to 6. Okay, so our ending discussion was a bit more involved than usual, but that's the nature of the beast, and after you do it a few times, it can actually start to make sense. Okay, thank you for listening. Good luck and God bless until the next lecture.